Okay, so looking at example 3.5, we're given the heat capacities of ice and water at 0 degrees Celsius, or whatever they are, and the enthalpy of fusion for water, of course, is a certain value, and then we're asked to calculate the entropy change for freezing 1 mole of supercooled water at 10 degrees Celsius. In other words, so what are we? So that's what we need to calculate. So we need to calculate delta S for the change for freezing water from liquid to solid at minus 10 degrees Celsius. So, and that of supercooled water. So there's actually liquid water at minus 10 degrees Celsius. So that's what the supercooled part of this means. So what are we looking at? So if we were to write it like an equation form, essentially we're looking at water in its liquid form at, so let's put it in brackets, minus 10 degrees Celsius going to water in its solid form at minus 10 degrees Celsius. Okay. And we're interested in calculating delta S for this process. Just interestingly, what do you expect delta S sign to be? We're going from a liquid to a solid. So in other words, there should be a decrease in the disorders. In other words, you expect it to be negative, right? Okay. Of course, you answered that on your own. I didn't help you at all with giving you the answer there. Right. So that's what we're looking for. But we're given the heat capacities at 0 degrees Celsius, not at 10 degrees Celsius. So that's a bit of an issue. And also the enthalpy of fusion will also be at 0 degrees Celsius. So how can we work around that? Well, this delta S that we're looking at here. So if we draw a little sketch to help us. So if we say water at liquid, so let's say water liquid at minus 10 degrees Celsius to ice, so let's call it ice, so this will just to keep our bearings, so that's a solid at minus 10 degrees Celsius, right? Let's give this, make this blue, let's make this red. No, it's not really hot, but just keep my bearings. So there's some delta S that we want to calculate here, right? We can actually calculate with intersteps in between. We can first, in a theoretical sense, that's not really what's happening, but we can first heat this water to liquid water at 0 degrees Celsius, right? So in other words, no phase change, 0 degrees Celsius. Okay. Then freeze that water to get ice. So then we have a solid at 0 degrees Celsius. And then cool that solid back down to get our ice at minus 10 degrees Celsius. Do you agree? That's exactly the same as taking the supercooled water directly from minus 10 degrees Celsius to ice at minus 10 degrees Celsius. We could heat the water to 0 degrees Celsius, freeze it at 0 degrees Celsius, and cool it back down. Well, cool that ice back down to 10 degrees Celsius. Right. So just instead of having one big process, we have 3 smaller processes. And we can call these, and we can sum their entropy changes to give us a large entropy change. In other words, then large delta S is equal to the sum of our smaller entropy changes. Okay, so that's how we break it up, and then we can use our standard information. Alright, so how do we do that? Well, this is not a phase change, this is from liquid to liquid, so this first one, so this is not a phase, so not phase. So in other words, for this change, we can use the equation 3.17. So that says then that delta S is equal to Cp. So this will be done at constant pressure because it will be done at atmospheric pressure, for example. Ln Tf over Ti. Okay, so we can calculate, so delta 1 is equal to that, or delta S1. This, however, is a phase change. So we need to use equation 3.15. We're going from liquid water to solid ice, so solid water, even though water or whatever. You get the picture. So we're looking at the enthalpy or the entropy of fusion. So the entropy of fusion is equal to the enthalpy of fusion divided by the temperature at which that, well, the melting temperature. Alright, so that's of course at 0 degrees Celsius at which that takes place. So delta S fus, so this is equal to, I'm just going to make a little note, so that's equal to delta S2. Okay, delta S3 is again not a phase change, so I should actually write here phase change. This again is not a phase change. Not phase. Right. So again we can use the Cp ln Tf over Ti. Okay. So that means delta S is going to be equal to, well, Cp, so what is it? Cp of liquid water is delta S1. So what did it say of liquid water? So the heat capacities of ice, so that's solid water, and water, so liquid water at 0 degrees Celsius. So in other words, we can use it for that. 4.18 joule per Kelvin per mole. So it's then 4.18 joule per Kelvin per mole, and then by how much that needs to be multiplied is by ln. Okay, so what's our final temperature? Our final temperature is 273 Kelvin, and our initial temperature is 263 Kelvin, right? Kelvins will cancel, so it doesn't really matter to write them in, but for completeness sake. Then our next change is our enthalpy of fusion, so which is 332, so 332 joule per gram. Should also get used to like different units, and that occurs at 0 degrees Celsius. So it's a phase change at a specific temperature, because phase changes occur at a certain temperature, right? Because remember the graph plateaus. So that's at 273 Kelvin. Alright. Oh, they gave us these in joule per Kelvin per gram. I just realized I made a little boo-boo here. That's a gram. Okay, all is good. Stop shouting. And then the last one again is that, and that's 2.2 joule per Kelvin per gram. 2.2 joule per Kelvin per gram times ln. What is the final temperature? The final temperature is 263 Kelvin over 273 Kelvin. Right. And then we just need to calculate these values. So the first one is 0.15598 and a bunch of numbers, joule per Kelvin per gram. Then it is minus 1.216 joule per Kelvin per gram. And then finally it's also minus 0.08299 joule per Kelvin per gram. Okay, which then eventually gives us minus 1.142 joule per Kelvin per gram. Okay, but now the question is that the final answer? No, because this is in joule per Kelvin per gram, and that is not molar entropy. Molar entropy is in joule per Kelvin per mole. So we need to convert that sort of, I don't really know what to call it. You can call it like, I'd rather just then call it something. So in other words, the molar entropy change will then be equal to this minus 1.142 whatever joule per Kelvin per gram times 18.02 gram per mole. Why that value? Because that is the molar mass of water. So in other words, the grams are going to cancel and then we get the per mole. So in other words, that's just how you flip it. So whatever you're working with to get it to per mole, and then that's going to give us a value of minus 20.6 joule per Kelvin per mole. Okay. So of course, as I said, and as we expected, this value is less than 0 because we're going from a less ordered liquid to a more ordered value, or more ordered state. So in other words, which is the liquid to the solid. And there's also some heat given off to the environment. We said everything here makes sense. Okay. So I think this is just a way to basically show you how you need to think about it. So you need to think about just this, breaking it up in, even though it says heat capacity of ice and water at 0 degrees Celsius, you use that information to calculate the changes between whatever from minus 10 to 0, and then you break it up into these little sections that we use. Actually, I touched on a little point there, but maybe I should explain it a bit better. So we're given these information at like 0 degrees Celsius, and we say the enthalpy of fusion at whatever. And then, so the only one that we really use, so the enthalpy of fusion we used at 0 degrees Celsius. You agree? I mean, there's no change between this 0 degrees Celsius and that 0 degrees Celsius. But if you look at these two, I mean, we're going from minus 10 here to 0 degrees Celsius there. And you might say, so how is the heat capacities applicable between 0 and minus 10? So how are we calculating this and this value using that, And essentially it's because we assume the heat capacity remains constant over that range. There are techniques that you can use. You can read in Atkins, for example, how you can vary a heat capacity over a range, but that's a bit outside the scope of us. In other words, if we give you a heat capacity, even though we say the heat capacity at 0 degrees Celsius It just means that is where the heat capacity is definitely confirmed, and you can sort of assume that in a given range, so plus minus a little bit, then that heat capacity is applicable. So in other words, just to make equation 317 applicable for you to use it. All right. I hope this example alleviated some stress, or makes more sense now. All right.